So today's lecture is about entanglement theory. Does anybody have any ideas what's entanglement? Yes?
If the system, if the Hilbert space of the system isn't fully separable for each component,
You mean separable as in a tensor product or separable as in infinite dimensional and not countable basis? So you mean the first thing, tensor product. So what you were trying to say is that the Hilbert space should be a tensor product of two Hilbert spaces, right?
if the problem can be described as separable, then well, the Hilbert space should be represented by this formalism.
Yes, the Hilbert space should be a tensor product of two smaller Hilbert spaces. The first one we call Alice, and the second one we call Bob, usually, or A and B. So what's entanglement? Yeah?
I would say entanglement happens when we cannot clearly separate the state of the combined system into the one part of A and one part of B.
Yes, exactly. That's the idea, that on this Hilbert space, we have some vectors that are unit vectors, so for example, psi AB, which is a tensor product of phi1 on A and phi2 on B. Right? Here I'm using AB to denote it belongs to this Hilbert space, and A to show that it belongs here, and B to show that it belongs here. And somehow here we can clearly say that, well, if we have this wave function or this vector in the Hilbert space representing the state of our system, Alice actually has this state and Bob has this state. So they're somehow independent of each other, non-interacting or something like that. And we call these states or these vectors either separable or product. Product because they're the tensor product of these ones. And entanglement, or we say that psi is entangled if it's not separable. So I cannot really tell you what entanglement is because it's defined by what it is not, and it's not separable. It's the complement of that. So if anybody tells you they know what entanglement is, like, I would be somehow very skeptical about that because we even define it as it's by saying what it is not. Okay, this works very nice for pure states, but we'll need to do the same for mixed states. Do you have any idea why we need to use mixed states? Yep.
Entanglement states will not be separable.
Yeah, I mean, there would be more states, more of them would be entangled, some of them would be separable. Yes, that's true. Yes?
You previously mentioned that we oftentimes cannot preparate our system accordingly. So this, well, yields a formalism including mixed states.
Yes. So somehow we'll now make that extremely explicit, and we'll see that entanglement plays a crucial role in that argument in quantum theory. But before we get there, we have to go through some other things. And the first of them is Schmidt decomposition. Which is a statement that for every this psi AB, which belongs to a tensor product of Hilbert spaces, there exists, so this inverse E exists, numbers lambda k, which are positive, and then on orthonormal basis alpha k in HA and beta k in HB, such that psi is given as sum over k equals to 1 to r lambda k alpha k tensor beta k. And here this somehow can be also denoted alpha k beta k if you want to avoid writing too many brackets. So this is just a mathematical statement about vectors in a Hilbert space, saying that if you give me a vector, I can always give you positive numbers and two orthonormal bases, such that this formula holds. The proof is rather straightforward, because by definition, we know that this psi can be expressed as a linear combination of the product basis, because this is how we even define the tensor product of Hilbert spaces. This is how I told you last lecture that you should define this object or remember what this object is. It's just by linear combinations of all of these vectors, right? When again, this I and j is vector I tensor vector j. And now this C is a matrix, and since it's a matrix, I can always write it in a singular value decomposition as UdV, where U and V are unitary matrices of some appropriate size, and D is a potentially rectangular matrix, but such that D is diagonal, and it has some positive numbers on the diagonal. Plugging the singular value decomposition here, one immediately obtains that we get sum over I, J, K, L, and now we just need to go through the matrix product. Okay. Now this we know that is lambda k delta kk. Ooh. And here we now get uki star I tensor j. This is of course on A and this is on B. Do you follow? So now just by applying this sum in here, this will become the alpha k orthonormal basis, and applying the j sum here, this will become the beta k orthonormal basis. Why are these two bases orthonormal? Yeah?
Because the I basis was and U is unitary.
Yes, exactly. Because we know that this is orthonormal basis, but more importantly because these two matrices are unitary. So in this way, we get exactly the wanted expression.
One question, could you switch the slides? Very helpful.
Yeah, thanks. Very well. Okay, moreover, we can define another thing, which is called the Schmidt rank of psi, which is just the smallest r, such that psi can be written as sum from k equals 1 to r of this lambda k, alpha k, beta k. So here the important thing is that this r is exactly here. It's the length of the sum. So then, if the Schmidt rank of psi is equal to 1, then, well, it's always pure, it's a vector state. Yeah, why?
It's only 1 alpha and 1 beta.
Yes, exactly. Then psi is essentially equal to alpha 1 tensor beta 1 and is separable. And moreover, note that you can always get the Schmidt rank of a vector by looking at this matrix, which you can always find by computing all possible inner products and then just doing the singular value decomposition. And if you actually want to do this in practice, you can use, I don't know, Python or Wolfram Mathematica or MATLAB or whatever. And it usually does this for you. So you just like call a function like go magic box singular value decomposition and you get free matrices. So it's rather easy to do this in practice and also reasonably fast. Okay, so far for theory. Now let's do something in practice. Let's prove that the state is entangled. So we'll take, so this will be an example. And I want to take a state of this form. So this is 1 over square root of 2, 0, 0, plus 1, 1. So both HA and HB are qubit Hilbert spaces with dimension of 2. This is the computational basis. And this state is called either the EPR pair or the Bell pair or the Bell state or something along those lines. How do you prove that it's entangled?
Non-separable. Or
Yes, but how do you prove that?
non-decomposable.
Yes, but how do you prove that? Yeah?
You compute the rank of the matrix 1 over square root 2, 0, 0, 1 over square root 2.
Yeah. How do you do that without a computer?
It's 1/2.
The rank.
Oh no, it's 2 because it's diagonal and the entries are not 0.
Yeah. That's a possibility. Is there like a more direct approach? Yeah?
I do not know if this yields a fitting example, but you could perhaps, mathematically speaking, make some kind of proof by denial, proposing it might be
By contradiction.
by contradiction.
Yes, exactly. How?
You could argue that, if the statement is true, that it could be accordingly to a Schmidt decomposition, and accordingly to our first proof, I think.
Yes, you're on the right track. So what we can do is that say, if this would be a separable product state or separable state, then it must be of this form. Right? By definition. And then we can say that, well, this vector belongs to HA, and we know it's a qubit Hilbert space, so it must be alpha 0 plus 0 plus alpha 1, 1. When alpha 0 plus alpha 1, their magnitude squared must sum up to 1. And the same here for beta 0, 0 plus beta 1, 1. And thus we get alpha 0, beta 0, 0, 0 plus alpha 0, beta 1, 0, 1 plus alpha 1, beta 0, 1, 0 plus alpha 1, beta 1, 1, 1. Now by comparing this expression and that expression, we get that alpha 0 times beta 0 is equal to 1 over square root of 2. And the same thing holds for our alpha 1 times beta 1, from which we get that alpha I is not equal to 0, not equal to beta j. In other words, none of these coefficients can be equal to 0, because if one of them is equal to 0, one of these products is equal to 0, which would be a contradiction. But then we also know that alpha 0 times beta 1 must be equal to 0, which is possible only if one of them is 0. So then we get a contradiction. Now, why I wanted to go for this proof is because somehow this already captures what we'll be doing later with entanglement detection, is that we somehow assume that if the state is separable, something would hold, and then we arrive to a contradiction. And it will not be this lecture, it will be next lecture when we'll be just using this logic over and over and over again to prove or to investigate entanglement of mixed states, right? For pure states, it's rather easy because you can always do it like this. You can always derive analytical conditions. For mixed states, it will be way harder, but somehow this logic will always apply. Assume your state is separable, arrive to a contradiction. So now let's move to the mixed states. And before we actually define entanglement for mixed states, let us look once again at the motivation for mixed states, because one of the things that I said is that we use mixed states because we work with noisy systems or with something like partial systems. So what's usually going on is that you have your atom or trapped ion or photon or something and sitting here. Is anybody working on experiments? No, you're all theoreticians. Okay. So this is a very much an atom or a trapped ion or something. And this is your system that you want to work with. This is your qubit. But what you usually have around is that you have like this big bad environment that's trying to disturb your system. You know, there's like air molecules sometimes trying to collide with your atom, or there's some radiation within the room, or magnetic fields, gravitation of the earth, whatever. And so instead of just working with the Hilbert space HA, which you in principle know very well, because this is what you somehow design the experiment around, you also work with something that's a state also of the environment, because what's going on is that your state also must include the environment, because our atom can entangle to the environment by interacting with the environment. But there's now a problem, because whenever we would want to describe experiment in this way, we in principle don't even know what the environment exactly is, because it can involve all of the air molecules in the room and all of the radiation bouncing around the walls and everything. We would have to prove stuff for all possible environments. So now what we will do is that we will show that if we are in this situation, we can reduce to a mixed state over the Hilbert space HA by somehow removing the environment by a trick called partial trace. And once we do that, we are left with a mixed state, which is somehow harder to work with, but we don't really have to bother with the environment. So it's like a trade-off. You might want to deal with a huge environment, maybe, and then get like easy results like this, except for now this is infinite dimensional Hilbert space, or you switch to just using density matrices on your Hilbert space. And most people go for density matrices because then you still have like 2x2 matrices and you can, or 4x4, and you can still do numerics with those. So let us look at partial trace. Did you by any chance do this before? Okay. So let's say I have an operator which acts on the tensor product of Hilbert spaces. As we already argued, tensor product of Hilbert spaces is a Hilbert space, so we can have operators on those. And then I can assume that the operators is such that C is equal to sum over AB, CAB, A of A times B of B, where A and B are operators on Hilbert space H, A, and Hilbert space B. And the CAB is not, don't confuse this with the matrix of the operator. This is small c, and it's just some coefficients in the decomposition. Is it clear how operator defined like this acts on vectors in this Hilbert space? Should be, because we already argued that all of the vectors here are just linear combinations of these vectors I and j in computational basis, and you can always act with this on the first one, with this on the second one, and then undo everything by linearity. So it works exactly as you would expect it to work. So we see that some operators on this Hilbert space are of this form, and I'll now argue that this is actually the same, and you can express every operator like this. And the way to argue that is to look at the matrix elements of this operator, because we know that we can now express this, and this is now big C, in this form, where what I'm doing is that I'm using the I and j as an orthonormal basis of the tensor product Hilbert space, and I'm just writing out the matrix of this operator in this basis with 2 indices. Now you can always see the 2 indices as one index, because if you have like 2 indices taking different values here, you can always sum in something like this kind of fashion to convert 2 indices into one index, or whatever path you want. And so just looking at what this is, we get, okay, this is on A, J, L, on B, and now by renaming the indices, this becomes the AA, this becomes the BB, this becomes the small CAB, and we get the expression above. This is important, this is like an important technical result, because it just tells us that if you have an operator on tensor product of Hilbert spaces, you can always decompose it in a basis that's a tensor product of operators. So somehow the stuff that we did here to define the tensor product of Hilbert spaces, now we get the same thing for the linear space of operators on that Hilbert space. And why this is important is because then we can use this for the first definition of partial trace. Which is as follows, that trace over system A of C is given as sum over AB, still using this definition, CAB, trace over A of A, B of B. And trace over B of C is the same as AB, CAB, A of A, and here we put trace on B of B. So this is the partial trace. This is partial trace over subsystem A or over Hilbert space A. And what you just do is that in this tensor product, you just trace the operator A, or the operator on the first Hilbert space. The second one, you just trace the second one. Now there is an obvious consistency problem. Anybody see it? Or potential consistency problem that we should in principle resolve. So the usual thing would be that here I assume that there exists the definition, this kind of sum of tensor products of operators that gives me my operator C, but in principle this is not unique. There can be many different sums, and if I want to use this definition for a partial trace, I should prove that for whatever decomposition here you take, you always get the same result here. And you can do that, and it's a nice interesting exercise, and like a small mathematical lemma to prove, to make yourself happy before you go to bed or something. But we don't have to do this, because we'll use a different, we can also introduce a different definition that doesn't depend on the decomposition, and then we will see that somehow we'll always get the same thing. So this is our definition 1. And we can now do definition 2. And we can say that trace A of C is a unique operator on the Hilbert space B, such that trace A on C and E is equal to trace C identity on A times E on B, or times the E. So what we are technically doing here is that in order to define this operator, we just say how it acts when we trace it against arbitrary other operator. And this is sufficient in principle for, you can see this in 2 ways. First of all, how you can see this is that in principle operators would form the Hilbert-Schmidt-Hilbert space. On the finite dimensional Hilbert space, this would be completely okay, and in this way you are simply defining a vector of a Hilbert space by how it acts as a functional. Or you can somehow assume that you can always put here projectors and all of these things, and you can somehow get the definition from there. So this is nice. Now we have 2 definitions. Now we have to prove that they are actually the same thing. So without loss of generality, we can just assume C is of this form, because we already argued that we can decompose everything else linearly in this. And then what we can do is the trace of this and identity times E. So what we now want to do is that we are now looking at this expression, and we want to express it in this way, where we isolate the E somewhere here, and the rest should be the trace the trace over A of C. So now multiplying these two terms, the identity multiplies A, the B multiplies E, and the way that the multiplication works like this, you can see by how we define the action of this operator using the tensor product of computational basis. And now we have here two traces. So then again, decomposing this in a computational basis, we get product of the traces. Where now you have to understand that this is not a statement about partial trace, this is just a statement about traces of operators. And again, if you would plug this here, the definition of trace using computational basis, so it's the sum of the diagonal, you would get sum over the index I and the sum over the index j, so it decomposes into two traces. Yes. And now we're almost there, because now we just need to reshuffle the terms. And what we get here is trace over A times B traced against E. And this we know should be equal to trace over A of C E. And so here comes the magic, that now this term is compared to that term. And we see that we are getting the same thing, because the first definition of the partial trace would just give you this thing, and the second definition of the partial trace is exactly coming from this equation up here. Is this clear? Is this too fast, too slow? Should I do some of the arguments more explicitly, or? Okay. So now, why is this relevant to our case? Is because if we have exactly the situation that we have a system A and subsystem E, then in general we have some kind of density matrix rho AE, which is a density matrix here. But in principle, we want to somehow keep in mind that we want to argue about pure states, but we don't really have to restrict the argument to that. And now, if we want to measure just the system A, what we are going to be computing is that we are going to be computing trace of rho AE over MA times identity on E. So here, MA is just P of EM on HA, so these are the operators that give us probabilities of observing certain events or observing measurement outcomes, as defined in the last lecture. If the P of EM acts only on the Hilbert space A, then this would be its extension to also include the environment, where we are basically not doing anything to the environment. And this is the probability that we want to compute of observing certain outcome of A in an experiment where we have a system A and environment E. And now, using the definition 2, we get that this is nothing else than tracing away the environment of this and MA. And this is where the magic happens. This is
one question. Your notation. MA equals what?
Oh, yeah, well, okay. In principle, the P of EM should be set of operators MA labeled by label A, which are positive semi-definite and sum up to identity on A.
right hand side of the equation, your notation P, where P, D, and which node or which?
This equation?
No.
He just doesn't know what a POVM is.
Oh,
PPM.
POVM,
Yes.
positive operator valued measure. So it's literally just a set of operators such that they are positive semi-definite and sum up to identity. If somehow you don't remember what they are, you can always assume that this is just projectors in an orthonormal basis. Okay, so this is not always, but these are called projection valued measures, or PVMs, and some POVMs are PVMs and not all. And you can always assume that, or you can always remind yourself that they could be of this form, and that's exactly because then what happens is that if we trace pure state against a projector like this, we get nothing else than the square of the inner product, which is just the possibility that we observe the outcome A of an observable with this spectral measure if we are in a pure state psi. Does that refresh the notion?
Right, but you wrote on the board.
Sorry, what?
But yes. Yes.
Okay. Yes. So this is how we arrive to density matrices, that if you want to work on a system A and you have some environment, and you will always have an environment because it's always going to be noisy, and that's the big problem in quantum information, dealing with the noise. You can reduce to just states of your system, but you pay the price that you have to go to density matrices because of this partial trace. Moreover, this you should see as some kind of effective state of the system, right? This is not something like some people make big arguments whether this partial trace is a physical state of the system that somehow exists. Some people make arguments that this is just a mathematical thing that exists in our heads, and one can have lengthy arguments about this, but somehow effectively describes what's going on with your system. And I don't know whether you prefer to have or not have those arguments, but it can be interesting reading or not, depends on your preferences. Also, interesting thing is that if we just restrict to the density matrices like this, we don't even have to care about the environment. So we just say that our state is a density matrix that's somehow decomposing or undergoing some noise process, and we in principle just forget about the huge environment, just model it somehow effectively through having a density matrix and through having not pure state, or through the loss of purity of the state. But now there's an important question to be had, because if I want to justify using density matrices like this, the question is every density matrix a partial trace of a pure state? Because if there are density matrices that are not partial traces of a pure state, then we can somehow forget about those ones, and maybe we can prove some stronger results or something. So this begs the question, are there density matrices which are not partial traces of pure states? Does anybody have like a guess or opinion? Well, so the question is, given a density matrix on the Hilbert space H, which without loss of generality we can write in the spectral decomposition, is there a pure state psi on some H tensor environment such that the trace over the environment of this guy is our original density matrix? How would you investigate these questions? Does anybody have an idea where to start? What to try? Yeah?
You start with the general state and construct a pure density matrix out of that, and then take the partial trace.
Yeah, exactly. That's a very good idea. Let's just see what this gives. And to do that, just take this psi and just say that, well, it must have a Schmidt decomposition, right? Which means that this pure state, you get this thing twice. But then the partial trace over the environment, or in this case, since I did not specify which one is the environment, I put here number 2, meaning over the second thing in the product of the psi is going to be ideas. We're going to be tracing this term, and what's that going to be? Trace of this.
1.
Sometimes. Yes?
Delta ij.
Yes. Why?
Because they're orthonormal, and in the trace you can permute.
Yes, exactly. So somehow what you get if you trace ij is that you get sum over k, k, I, j, k, and this gives you delta ik, this gives you delta jk, and these two k's, they just contract each other through the sum to delta ij. So we just get eta I squared psi I psi I, which, well, already looks kind of like this. So in order to reverse engineer the correct state psi, we can just write what? If this is squared, that's going to be square root. So we can just go on the I square root, phi I, tensor I. And this psi, well, this psi should be with a tilde maybe, so we don't confuse it with this psi, because now this psi is that psi that we are actually looking for here. And this base can be arbitrarily chosen. Here I'm taking a square root. Is it a problem or not? Why? Like, you know, if you take like a square root of I, that's not uniquely defined and things like that. So could this be a problem?
In the Schmidt decomposition, the lambda were positive.
Yes, but these lambdas are actually the eigenvalues of the density matrix. So, but they're still positive, and you can just take the positive thing here. And since you square them, you can also sprinkle in some minus signs if you want. Doesn't really change a thing. Well, the last thing that we should check is whether this is normalized vector, which you can somehow get out of the properties of the density matrix. So the main idea of the first, say, half of the lecture is that, well, everything would be simple and easy with pure states, but our systems usually interact with an environment because quantum systems are very hard to isolate from everything else. And this causes them to entangle with the environment. And if you don't want to deal explicitly with all possible environments, you can use density matrix description to get rid of the environment, but you pay the price that you're using density matrices. And moreover, you have to use all possible density matrices because every density matrix can arise as a partial trace of some kind of entangled state, entangled pure state, that is. So now we finally get to the interesting part, which is entanglement of mixed states. This is where the stuff starts getting interesting. So now we can say that the density matrix on the tensor product of Hilbert spaces Well, it's separable if... What should I put here? What do you want to put here? I clearly should be consistent with whatever was probably written here before I erased it. If this would be a pure state, what would be here? Yeah.
Would be the tensor product of two states.
Yes. Where this is density matrix and this is a density matrix. But now we have the problem that we can get additional randomization through things. So we get this form where this pi is a number. So pi is a real number. Moreover, it has to be positive. And sum over I of pi is equal to 1. This is just normalization condition. And sigma I A is a density matrix on HA. Omega I B is a density matrix on HB. So we define what's separable, and we defined entangled states as those that are not separable. So in other words, we define them as a complement of whatever separable means. There is a very nice intuition behind this definition, which is, other than the one coming from the pure states, is that these are somehow states that Alice and Bob can prepare through what we call local operations and classical communication, which basically means that Alice and Bob can call each other or send messages on WhatsApp or Telegram or whatnot, and they can perform local operations in their labs. So they cannot exchange quantum states, they can just exchange classical communications, emails, but they can do whatever they want in their labs. And then you can somehow persuade yourself that in principle they can prepare any state like this, because they can in principle somehow randomize and draw a random number based on this distribution pi, and based on the number I they draw, they prepare the states sigma I and omega I. So then you can also say that separable states are those ones that are LOCC preparable, or it's a in this way. And this LOCC definition is somehow nice, because this is something that you would use in quantum protocols to talk about entangled states and saying like, oh, if we have Alice and Bob that are somehow separated, so they cannot exchange quantum states anymore, but they have some entanglement between them, can they do this based on an LOCC protocol? Now, important thing is that this pi is positive. And you cannot easily drop this condition. I'm not mentioning this because this would be somehow a deep result, but I'm mentioning this because it's a easy mathematical mistake to make. Actually, it holds that if you have arbitrary, so for all rho AB as a density matrices, you always have that this can be written as sum over I of some coefficients qi, sigma IA, and omega IB, where this qi just sum up to 1. So if I drop this positivity condition, this decomposition exists for arbitrary state. The way to prove this is that if I have an operator A on, say, Hilbert space A, then I can always write it as a sum of the positive and negative part. The positive and negative parts are positive semi-definite operators, and what's going on here is that I can always isolate the positive eigenvalues of A here, I can isolate the negative eigenvalues of A here, and then I pull out the minus, so everything here will be the absolute value of the negative eigenvalues, and in that way I can uniquely decompose A into a positive part and negative part and their difference. In case it's not clear, you can always tell me and I can write it down explicitly. And then we can express any A as trace of A plus, sigma plus minus trace of A minus, sigma minus, where sigma plus minus is nothing else than the positive or negative part divided by the respective trace. So we can you can write any operator on a Hilbert space A as density matrix times something minus density matrix times something else. So then when we have arbitrary density matrix, we know that we can always write it as sum over AB of this CAB of some AA times BB. And what we now do is that we just plug in that expression, and so we get trace A plus, and here's something sigma A plus minus trace A minus sigma A minus. Tensor the same thing on omegas. And if you undo this, you basically arrive to the composition like this, because all of the operators that you will now have here are density matrices. So there'll be this, and all of the coefficients you just collect together and just call them Q. So this condition extremely important, don't forget about it. And this is how entanglement works. This is in principle all you need to know. Now the question is that how much entanglement can we have between different systems? This is in principle an important question, because in practical protocols we would want to have as much entanglement between everyone as we can, but turns out that quantum theory somehow limits us here in how entangled we can be with everybody else. Or rather, that if you want to have too much entanglement, then you also have to have a large system or many qubits. And the result that characterizes this is known as monogamy of entanglement. And this says that if we have a density matrix onto Hilbert spaces, such that trace over B of rho AB is a pure state. This should be psi. Then rho AB is just some density matrix on A times the pure state. No. Sorry, other way around. It's that pure state on A times the density matrix on B. And this has somehow a deeper meaning, because this tells you that, well, in principle, if I want to be in a pure state, which means that, for example, I want to share the bell pair between Alice and Bob, so we can somehow, or Alice and Charlie, so we can somehow say that this is A and C together, then we cannot share any entanglement with Bob. Or we need to use different qubits to entangle with Bob. Or it also tells you that if you have a system and you actually make very sure for your system to be in a pure state, you can literally forget about the environment and you can just deal with standard quantum theory with wave functions instead of density matrices. Let's prove this, shall we? So this proof is not very hard, but there's going to be several hoops to jump through and several manipulations with partial traces that might be maybe new if you're not used to them. So if you're interested in this, I somehow maybe recommend going through it later and looking at it and making sure you understand all of the steps if you're interested in this type of research. If not, then you can just maybe take like a 10 minutes break until I explain the proof. So the first important realization here in the proof is that this is the same as putting two identities here. And if I take an operator E on B, which is between 0 and 1, so this means that E is positive semi-definite, and this E of B less than 1 of B is the same as saying that if you subtract this, that 0 is less than identity of B minus E of B, where it just means that this difference is positive semi-definite, and you already know what that is. So if we have an operator between 0 and 1, what we get is that this can be written as trace of B, rho AB, identity on A times E here, plus this. So all I just did is plus E minus E here. Now, why I wanted these conditions? I wanted them to make sure that the E I have here is positive semi-definite, and that the thing that I have here is also positive semi-definite. Because we then get that this partial trace must be an operator, this partial trace must be an operator. And since this is positive semi-definite and that's positive semi-definite, it must be a positive semi-definite operator. Oh, and the fact that, for example, this is positive semi-definite operator can be proved by saying that, okay, I can prove it's positive semi-definite by showing that its trace with any positive semi-definite operator is bigger than 0. So we define positive semi-definite by saying that if you sandwich it with two vectors, with the same vector from each side, it's going to be positive semi-definite, and it's the same as saying that this trace is going to be positive semi-definite, because you can always assume that I just put psi instead of f here. This is just a bit more general statement. And how to prove that this is positive semi-definite? Well, just use our previous definition. So according to definition 2, we just can get rid of this partial trace, put the identity here, and we get here rho AB and identity on A times EB, which is what we have there. And this is F on A, so we don't forget where it is. Which is nothing else than just multiplying this out together. F on A times E on B. Now, we assume that this is positive semi-definite up here. We assume this is positive semi-definite because that's how we want to prove that this thing is positive semi-definite. So what we have here is a positive semi-definite operator multiplying a positive semi-definite operator and their trace, which is again going to be positive number. And from this, we get that the thing inside here is positive semi-definite. That immediately implies that this other thing here is positive semi-definite, because it's essentially the same proof except for you replace the E with the 1 minus E. Good. So now we can say, and this somehow should be seen as a portal going from there to there. Now this is something like lambda times sigma A plus mu times omega A, where lambda and mu are positive numbers, and sigma A, omega A are density matrices. Yeah, but that's nice, but we now have to look at what we had at the beginning, because we already know what this is. This is nothing else than our original pure state. So this is nothing else than this thing. So I already explained during the last lecture that if you have a density matrix, it's going to be a convex combination of pure states because of the spectral theorem. Now the inverse result holds as well, or the inverse result, the other way to define pure states is to say that if a state is such that I can express it as convex combination of different states, and all of these different states have to be actually that state, then it's pure. So this is more like a convex geometric definition of extreme point. So what I'm just saying is that this implies that sigma A is equal omega. Well, first of all, by tracing, this implies that lambda plus mu is equal to 1, because trace of this is 1, trace of this and that is 1, so lambda plus mu equals to 1. And then it implies that, well, what I have up there is just lambda sigma A plus 1 minus lambda omega A, and this implies that sigma A is the same as omega A as is psi, and this is exactly because the psi is pure. This, in other words, just states that pure states are the extreme points of the set of density matrices. If you had convex geometry, it's just an extreme point. But since we, in principle, since we did not define it like that, we have to actually prove this. And we prove it by sandwiching this with psi from both sides. So what we do here to this equation is that we put psi here, everything else here, and then another psi here. And we get that 1 is equal to lambda psi sigma A psi plus 1 minus lambda psi omega A psi. Now, we know that these two numbers are positive because density matrices are positive semi-definite operators by definition. And I now claim that this already implies that this is equal to 1 and that is equal to 1. Why? Yeah?
I guess because that's the only way for the scalar product to be 1 to resolve the equation.
Yes. Or in other words, if lambda plus 1 minus lambda is already equal to 1, and I would multiply it by something less than 1, the sum would be strictly less than 1 as well. So this is like a high school or middle school math result. So we get that this thing is equal to that thing is equal to 1. And this already implies that, because this means that the density matrix sigma A in the So a cheap argument here is that I can always write down a basis where psi is the first thing in the basis, and then I have some other orthogonal vectors or orthonormal. And this just means that psi A in this basis would have 1 here and then different numbers here. But since I know that trace of sigma must be equal to 1, I get that everything else down here must be equal to 0. But since sigma A is positive definite, I get that everything else around the zeros must be equal to 0, because once you have a 0 on a diagonal of a positive semi-definite matrix, the whole row and column will be 0. Otherwise, it's not positive semi-definite. Okay, so what we are getting here is that the sigma and this omega, they're actually the original psi, and moreover, they don't depend on the choice of this E. So the only thing in this equation that we are getting here that can depend on the choice of E is this lambda. Because remember, this mu is just 1 minus lambda. So this lambda will depend on the choice of E. This mu will be just 1 minus lambda of E. And everything else is independent of the choice of the operator E. This lambda depends on E. How do we now express the lambda out of this everything? So what we now want to say is that this lambda as a function of E, well, it's a linear function because it comes from this expression. And what we would want to do is that we want to write it in some kind of fashion like this, because every linear function can be written like this on operators. But to do this explicitly, what we can do is that we know that lambda of E times psi, which is the first term here, is nothing else than this. So this is just trace over B of rho A B, identity A times EB, and one more thing. So now if I want to get the access to this lambda E, I can again sandwich it with the psi. So psi comes from here, and I get psi trace B rho A B identity A times EB. Now this is the part where it gets fun, or where it gets tedious, depends on what you call fun. Because now I can say that if I put in this inside the trace. So using the trick that this thing is trace of A psi psi, over here I get that this is the trace over B, rho A B, identity on A times EB psi psi. So just this goes inside the trace. Now using the definition 2, you can now get rid of this partial trace over B. So what we get is that we get identity over B here, and this can multiply that. So we get rho AB, and we get psi psi times EB. And now I want to do the same trick, but on the other side. So in inverse. So I want to then write that this is the same as trace over A, rho AB, psi psi times identity EB. So going from here to here is the same trick as going to here, but read backwards and on a different subsystem. Is at least the idea clear? Well, so this is the X we were looking for. Yes, that one. Now finally we can make an argument that if I take this rho AB, and I now just want to take two arbitrary positive semi-definite operators, FA and EB, and I want to see what I get out of this. And I argue that what we can do is that we can first do the partial trace over the EB system and pull the FA out. So essentially, again, the same trick as we used around here, and then plug in this result, or rather this result, and we just get that this is nothing else than lambda of E, and trace with this psi on F, which is again nothing else just by plugging the value we have for lambda of E, that's trace XE times trace of psi F, and that's nothing else than the trace of X tensor psi, and here's sorry, other way around, psi tensor X F tensor E. And now it's done. Now it's finally done. This is what we were looking for. Because now we know that for arbitrary operators that you put here, this trace is equal to that trace. Which means that now you can, from this, deconstruct that this operator must be equal to that operator, for example, because their matrices would coincide. If instead of arbitrary operators, I would start putting here elements of the computational basis and so on. So in other words, we get that rho AB is equal to psi tensor X, and this X now becomes actually our sigma would be as it's in here. So in principle, you don't really have to know this proof, you just need to know the result. But I think it's a good exercise to understand the calculations in the proof so that you can do them easier in the future. Any questions? So now here's the problem again, that usually if you want to perform some algorithm with quantum computers, for example, some cryptography based on violations of Bell inequalities and so on, you would usually want those Bell states or EPR pairs that we had before, because somehow this is one of the most well-studied, most used states in all of quantum information. So that's psi plus that we had like at the beginning of the lecture. The question is how to get them, because if you want to create them, that's possible, but then the problem is that you would want to somehow send one of the qubits, which is usually a photon, to Alice, which can be in Berlin, and you can send the other one to Bob, which can be in Frankfurt, and by the time they get there, they're completely noisy, because then again they entangle to some kind of environment and so on. So how do we fight all of this noise? And here comes the idea of entanglement distillation. So the idea is that we want to have psi plus, which is again this 1 over square root of 2, 0, 0, plus 1, 1 between Alice and Bob. But we get rho AB, which is a potentially noisy mixed density matrix, but hopefully still entangled. Moreover, we don't just get this once, because if we get it once, we can just get it again and again and again and again. So we get many copies of the same state. And people then usually say that they know this as a tensor power of the state, right? So this tensor product up here, it's like a tensor power. It just means do tensor products of many times. And so now Alice and Bob get many copies of this state. They cannot somehow magically pull out these states out of their pockets. They just get this. But what they can do is that they can use local operations and classical communication, which again means that Alice performs whatever action she wants in her lab, tells the result of her action to Bob, Bob performs another action, tells the result to Alice, and this can go on and on and on and on, back and forth. And the question in entanglement distillation is whether we can use LOCC transformations to transform this state to the Bell pair that we want. And if yes, then we call the state rho AB distillable. If no, we call it bound entangled. So yes, then rho AB is distillable. No, rho AB is bound entangled. And now there are several results. The first one is that bound entangled states exist. The second is that every separable state is bound entangled. But also, there are bound entangled states which are not separable. And actually some people say that in order for a state to be bound entangled, it cannot be separable, and some people include separable in the definition. Just make sure if you're reading a paper to understand what the authors are talking about. But overall, the picture is like this. We have the set of all states, and then somewhere around here we have the set of separable states. And then somewhere in between here, we have the set of bound entangled states, which are not separable. And so, as you can see here, all we did so far in the definition of entanglement was for just two parties. So we were considering we have Alice and Bob. Now the question is, what happens if we have Alice and Bob and Charlie? It's actually somehow important to remember. Who of you wants to maybe do a PhD and do research? Okay, so here's an important message, or like a moral of defining entanglement, is that we already know how to do it for two parties, and we can publish now papers about entanglement between two parties. But since as a scientist we have to publish many papers, we can also try to investigate essentially the same problems for three and more parties and publish even more papers. But actually it's not so bad, because multipartite or tripartite entanglement is not just a trivial repetition of the bipartite case. So the bipartite case is when you have two parties, tripartite, three parties, multipartite, more parties. So multipartite entanglement. And Now here's the thing, how to define this. Ideas. Say I have 3 Hilbert spaces, A, B, and C. I can do the same for more, but it's just going to be somehow more options. Yeah?
We demand that the state be decomposable into a tensor product of 3 states.
Yes. Very well. This is what we call fully separable. Any more options? We can also define something as a biseparable state. But we now have to say with respect to what bipartition. So we can say that, well, we can treat B and C as the same system, and then we can say that this is A with respect to the A and BC bipartition separable or biseparable if it's of this form. We can do the same but isolating B. And now observe that this is the reason why I keep writing here the letter of the system, because in principle this is a vector on HA, tensor HB, tensor HC, but this is a vector on HB, tensor HA, tensor HC. Somehow the isomorphism between these two things is obvious, so we're not going to write it and we're just going to say that it's equal, and we are going to keep track of what's on which system by just putting in the letters.
You meant AC, right?
Yes. And CAB, which is again the same thing. Wait, where again this isomorphism is here. And finally, we don't have just entangled states, because obviously the biseparable states can already be entangled. But then if it's none of these, then we call it genuinely multipartite entangled. Multipartite entangled, or GME. And an example of a GME state is, for example, the GHZ state, which can be this one. And you can actually prove it's a GME state by doing essentially the same thing that we did at the beginning for the bell pair. Or the W state. Oh, by the way, this GHZ stands for Greenberger, Hornet, Zeilinger, which is good to remember. And this W does not stand for Werner. Does not. No, because there's also something that's called Werner states, and it's not this one, it's something else. Good. And you can also say we can have n qubits, at which point you can define the GHZ state on n qubits, which is the same idea, just many more times. And now you can see that the GHZ state on 2 qubits is the bell pair that we had before. And GHZ states are something that's also very common in many protocols. Very well, finally we have to do the same thing again for mixed states, and now there's going to be even more options. Mixed states. What are the options now? Just reading that thing, there's of course the fully separable. where this is again some probability pi, and these are free density matrices. We can have A, B, C biseparable, which is essentially the same thing, but you now group the other two things together. And we can have again the BAC and CAB biseparable. These definitions, I hope you can write down yourself. And then there's something that we call just biseparable. Well, we call it without the just, but it's just biseparable. And this is if your state is with some probability state which is biseparable with respect to A and B, C partition. With some probability, it's biseparable with respect to the other partition. And with some other probability, it's biseparable with respect to the last partition. So the biseparable things include these ones, and these ones, and they're convex combinations, because you can randomize between what's going on. And then we have, again, genuinely multipartite entangled, which is not biseparable. And somehow the picture people usually draw is that we have something like fully separable states here, and then we can have the A, B, C here, and we can have the B, A, C here, the C, A, B here. This would be the biseparable, and these all are genuinely multipartite entangled. But please take this as a sketch, not as a true geometric picture. So in the end, we can also again talk about distillation, where the question now is that given many copies of the state, can we use LLCC to transform it usually to some form of GHZ state? And it's the same problem as before, just with more parties. The interesting thing is that there exist states which are multipartite bound entangled, so somehow you cannot distill GHZ state from them, and it's somehow non-trivial. It's different than when we did it with two parties, because there are states which are biseparable with respect to any partition, but are not fully separable. So they're of this form, they're of this form, and they're of this form, all at the same time, but not fully separable. And these states lead to multipartite bound entanglement. So now maybe to tease the next lecture is that now we know what entanglement is and how it works and why we want it, because in principle we want to distill states and then get GHZ states and we use those in protocols. Now the question is, how do you prove that a state is entangled? So how do you prove that a state is separable? Well, you write down the decomposition, you know? You write it down as the correct decomposition. But now, how do you prove that it's entangled? It's kind of a problem, because you would have to prove that the decomposition doesn't exist. But how do you prove that it doesn't exist? Like, how do you prove that I don't have a dinosaur at home? I might. And that's going to be the point of next lecture, because what we are going to do is that we are going to talk about entanglement detection, where we are usually going to say that, look, if your state is separable or of this or that form, then this holds for it. And if you give me a state and I check this and it doesn't hold for it, it cannot be of that form, because if it would be of that form, it would hold, but it doesn't hold, so it's a contradiction. That's going to be the whole point of entanglement detection. It's going to be the same logic as the one example I showed in the beginning. And please, you don't have to do anything, just if you want to follow next time, please think a little bit about this logic, that we are going to assume something is separable, then we are going to prove some consequence of that, and if the consequence does not hold for a given state, then it cannot be separable, because that would be a contradiction. Yeah, thanks.